everyone. My name is Tania, and I'm going to be talking about machine learning scoring, but rather focusing on scoring and predictions and accuracy of the model. I want to focus more on the quality assessment, validation, and testing of your machine learning systems, and focusing so much more on the adequacy and the integrity of them. At the moment, I work as a developer advocate for Microsoft, but before that, I've been working as a research software engineer, a machine learning engineer, and data engineer in different research organizations and also other businesses, trying to help them make their processes more reproducible, more robust, and deliver better and more efficient machine learning solutions. There is my Twitter handle, and I want to try something today. If there is something interesting that you learned during the presentation, or if there is something that you want to share, please use my handle there and tag me. And just a brief disclose of what we're actually going to cover in this talk. I'm going to present some approaches to machine learning systems and how they should be quality checked and assured for data validation. I also want to establish clear responsibilities when it comes to machine learning system testing and monitoring, and allow you to take this back to wherever you're working, whether it's a startup or a big company or a research institution. I'm not going to cover in-depth technical engineering best practices, so I'm not going to be teaching you how to actually implement a test of a machine learning system or a given machine learning algorithm, because that will change depending on the use case. And it's not going to be a very deep dive into these aspects. So let's start on why we actually need to test these machine learning systems. I want you to think back on any time that you created a new model or a new algorithm and you thought that was ready to take into production, but it just so happened that when it was there, it didn't work as expected, or it just didn't work at all. This happens more often than not, and often the responsibility of taking things into production from an R&D environment relies on the data scientist. Something that we also have to keep in consideration when working with machine learning is that these systems are continuously evolving. They're not single create and deploy solutions. So we're constantly learning from new data. We're constantly aggregating different new streams of data. Ideally, you would be retraining your model so that you improve the accuracy and efficiency for your customers. And also, well, you can see examples like this in which the failures of your machine learning algorithm or your model are not fatal, but more down the funny side of things. But if you're working in a very highly regulated environment like healthcare or finance, then all of these errors and all of these continuous degradation of machine learning systems and models can add up to very, very serious consequences. And ideally, we all should be doing quality control and quality assurance before our products even reach production and even before our customers start consuming them in any way. Because on one hand, it will ensure that we can increase the reliability, people can rely and trust what we're actually telling them that our algorithm is doing, and we can also spot bias and prevent our systems to be biased. Once our models have reached production environment and our customers start actually consuming it, we have to do, again, quality assurance, quality control, because that way we can evaluate the performance of our systems, of our models, and also monitor the integrity. Again, as I mentioned before, we're constantly aggregating new streams of data. We're constantly retraining our models and developing newer versions. So this is more essential than ever. And every time I talk about this paradigm of testing machine learning and quality assurance, people often tell me, well, so how is this different from testing any software? Or why should you even be talking about us testing machine learning? In a more traditional software engineering world, you have your software or your application or your solution. So as you pass some sort of input through that, whatever this looks like, it can be a data, numerical data, categorical data, you know what outcome or what result you're going to get out of it. So you always know what kind of data and what expected value you're going to return, so you can implement unit tests in a successful way. So for the most simple of cases, if you have a function, for example, in Python that is creating the summation of two integers, you can assert that, for example, 2 plus 2 is going to give you 4, and test those cases in which this test is going to fail. And it would be very, very nice if machine learning algorithms or machine learning models behaved just as nice or just as simply as software engineering, well, more traditional software engineering applications. But in real life, machine learning systems look something more like this. Normally, we would have the results and the data together. So if you're doing, for example, a simple classification algorithm, you already know what labels you're looking for. If you're trying to identify whether a fruit is an apple, a banana, or a pineapple, then you know that those are your labels. And also you have your historical data that you're going to use through whatever machine learning system to train your model. After that has been trained, then you have that numerical model that is actually trying to describe or predict the behavior of a complex system. And the only way we can, or our customers can consume said model is by feeding it new streams of data. And again, that data in conjunction with the model goes through machine learning systems to retrieve the predictions. So as you can see, it's not as simple as having one stream of input, one stream of output. And this definitely changes and makes it more complex to identify at which point I should be testing and what I should be testing in my system. Shall I just be testing the algorithm during the training before actually generating the model? Or should I be testing the system between training or after training and before predictions? Or shall I be assessing the predictions and having unit tests? It becomes much more complex than just having a single input output being processed through a simple solution or a single solution. So in order to identify and learn what we should be testing, we have these 4 categories that I always refer to. The first one refers to data and features, because these are the things that are the most important during the research and development stages. That is what your data scientists or us as data scientists will use to develop these models to describe complex systems. So in this area, we should take special consideration to test the data streams and test their integrity. The integrity of our data is vital for the life of our systems. When it comes to model deployment and model development, we also have to make sure that there are no bugs or any errors, issues that are trying to go into production, because they cannot be easily identified in a research and development environment or in a sandbox environment. So you really need to prepare the models for production-ready stages. Also, because now the machine learning systems are very complex and often rely on, for example, on cloud solutions, databases, ETL aggregators, and things of the such, we also have to verify the integrity of our infrastructure. We have to ensure that this is not decaying and it's actually sufficiently robust to handle the requests of our machine learning systems. And finally, we also have to keep an eye on the tests and monitor them frequently, just to ensure that by aggregating new streams of data, we are not getting weird relationships between the data and the model. During the rest of my slides, I'm going to be focusing on the first 3 stages, but if anyone wants to discuss monitoring of machine learning later, I'll just be around the conference. Now we know what we should be testing, or what areas we're going to be focusing, but also we have to define clear roles and clear responsibilities. In a team, normally you would have, or you can have, for example, a data scientist or a machine learner or a deep learning scientist. Then you would have a software engineer of some sort. That can be a software engineer, machine learning engineer, data engineer, and an infrastructure team or an IT team. So these testing responsibilities are spread among the three teams or among the three stakeholders. And each of these persons should be responsible for this specific area in which they can actually provide expertise domain. So before moving on and actually giving you a rubric or a clear definition of what you should be looking at on every stage, I just want you to think about your machine learning systems. If you work as at a startup or a company or as a consultant, I want you to think about what you're actually doing and implementing today. I'm going to give a few concrete steps. So for each step, if you're already doing some sort of manual testing, assign a point to these tasks. If you have some sort of automation or your company has some sort of automation, add an additional point. So for each of the points that I'm going to present for data, deployment, and infrastructure, you can have up to 2 points. I'm not going to ask for individual results, but I do want you to think about what is your current state of your systems. So let's start with features and data. And I like this phrase because this is very, very true in machine learning. The only way we drive new machine learning is by continuous feedback. The systems and our models and everything are continuously evolving and learning from new data streams, new data collection, better representation of our systems in different databases. So the very, very first test that you should be doing while developing a model is just verifying that the distribution of your features actually match what you should be expecting of them. If you're using, for example, expecting a Boolean variable, are all of these distributions as you would expect. In the very, very well-known case of the iris dataset, if you are evaluating or looking at the sepal width or the sepal length, are these actually represented in centimeters or millimeters? Or is it a weird kind of representation in meters or kilometers? Just make sure that all your features look as they should. Then it is a very, very common thing that finding features that will probably improve the performance of the accuracy model. Once we identify them, we just add them, or a lot of people feel the need to add them. But we also have to take into consideration the cost of each of these features, because sometimes we'll have a marginal improvement in performance, let's say a 0.01% improvement in performance or improvement in accuracy, but then that can lead to a very, very big increase in latency or a very big increase in the memory that our systems are consuming. And then you have to make a very, very important decision whether this increase in performance or accuracy is justifiable in terms of the resources cost that it's going to imply. Also, having more features also mean a larger number of dependencies upstream and downstreams. If to have this one feature, you have to aggregate another set of data, then you have 2 sets of data that you have to do quality control and assurance on. So consider all of this before actually selecting your features. The next thing that you should be looking at is the privacy and control across the entire pipeline. As a data scientist, something that we feel very tempted to do is only focusing on the raw data, because the raw data, if you're working, for example, in a bioinformatics or in a healthcare solution, that's where you have all the identifiable data, all the data that can help you to identify or pinpoint individuals. So a lot of people focus on that very early stage to anonymize and then do initial cleaning. But afterwards, then you start doing more manipulations, more changes, you move data from one side to another, you pass that to models, and then that is retrieved. But each point of your pipeline is very susceptible to security breaches, very susceptible for attacks. So you have to ensure that your security and your quality measures are covered from the very early stages of data acquisition, then transformation, and finally, model training and deployment of the model. Something else that people often forget about is data lineage. And this is very intimately related. At every point in your pipeline, you should be able to look at your data and know where your data is coming from, where it is going afterwards, and what changes or transformations have been applied to this. One of the most memorable examples that I like referring to when talking about data lineage is water transformation plants. If you have, you know that the water has not been through filtration processes because it has very unique characteristics in terms of color, smell, additional solids or things that might be there. But once it starts going through the processing plant, every single process will modify substantially the properties of water. If it goes through initial filtration, probably it's going to be cleaner because it's going to be removed from those solids. That is the same that we do with data. Probably we're removing identifiable information, but it goes somewhere else, and we have to ensure that the next steps are as safe as when we acquire the raw data. So that's something that we have to take into consideration. And this brings us to test every single piece of code that actually generates your features, that does any sort of data manipulation. Sometimes we think that, yes, the initial data preparation stages are very involved and very time-consuming, but sometimes people believe that because it's done and it's a relatively simple process in comparison to develop a novel algorithm or a novel model, then they should not be quality assured. And as I said before, you should always know what you're expecting from your data. Establish clear contracts between your systems and your data. If you're expecting to see, again, a data point or a data observation that can be categorized either as male or female, ensure that all the observations that are there are either in one of those categories. And have also very clear contracts on what is happening when this is not satisfied. What if instead of having, for example, 3 classes, as we would expect to have in the Titanic dataset, that is first class, second class, and third class, and we have some weird data observations that are pointing to a non-existing class? What is going to happen? What processes do we have in place so that our systems don't fail silently or just don't fail at all? And there is, for example, one of these libraries in Python called Rate Expectations, and this is a very good first start for you to start establishing contracts in terms of size, shape of your data, what kind of values you are expecting from it, and how you could probably breach those contracts. So the next stage that I'm going to move now is into model development and model deployment. So this is actually once the model has gone through the initial part of research and development, training, how do we ensure that it is production ready and the quality is of sufficient high level to be taken into the consumer's hands. And the recipe for this is best practices. Software engineering has a very clear set of best practices. Use version control, have tests in place, do code reviews. But we're still kind of determining what are the best practices for machine learning. We can adopt a lot of this from software engineering, but more often than not, when I work with different teams and I ask what kind of version control system they use or whether they do code review, so many of these teams don't use any of these approaches. So we need to start enforcing them at all points in our machine learning pipelines. So this takes us to every single piece of code, no matter if it's for cleaning, no matter if it's the model or an algorithm or production-ready code, everything has to go through peer review. For the junior data scientists or junior developers, this will be a very good introduction to our company style guidelines. They can see how other people are writing code, how they actually name variables, how, which format the code should be in. For the most experienced one, it is for the most experienced developers or the most experienced data scientists, it's a very good opportunity to introduce, again, best practices and work in collaboration with the juniors to set standards for the new work. Also, when we're talking about hyperparameters, we know that these are extrinsic properties, thank you, of models that cannot be a priori inferred from data. So also, make sure that you know what is the impact of each of your hyperparameters. Approaches like grid search can be very, very useful when you're trying to evaluate this cost and the impact, because they can also help us identify hidden reliability issues. Sometimes when you parallelize or try and optimize code or try to optimize machine learning algorithms, it turns out because it's been parallelized and the accuracy or the predictions change. If that is happening, then we have to do further debugging to understand why these changes are occurring and why and how we can prevent them, how we can make our pipelines more reproducible. Also, while we're talking about dynamic machine learning systems, we have to test for model staleness. If you remember, this is the schematic that I presented at the beginning. But how often do you retrain your models? Does it make any difference having a model that was trained 2 years ago, or 2 months ago, or last week? Are you expecting to see different results? And if so, is this what you want? How often are you replacing your models? Do you have some legacy models that probably you have the code in production, but it's nowhere to be seen in GitHub or in GitLab or any of your version control systems? Probably you should look at all of that. And also, you have to evaluate for model decay, because there are certain models that are going to present decay. And you also need to be prepared to take them off production and replace them with a more suitable solution. Something obvious, but that's not always done, is test your sophisticated models and validate them against a more simple model. For example, is this new, very fancy deep learning algorithm give you a much better performance than something as simple as logistic regression? If the difference between these two is marginal, and the cost of resources and utilization of resources is very, very big, then you have, again, to reevaluate which is the best approach for your company, for your solution, and for your customers. The next thing is to test the model for implicit bias. We've heard about implicit bias a lot recently. And this is because sometimes we didn't have enough representation of our system in our data sets. When testing or training a data set, you have to still do slices of your data, do more sophisticated testing to ensure that you're not further reinforcing systems that are biased. And if they're biased, you have to put in practice some measures to prevent this from reaching the customers or reaching society. And the final thing that we have to test is infrastructure. And I'm not going to talk about how to test your Kubernetes cluster or how to ensure that your Terraform descriptions are OK, or how to write more efficient Docker containers, but actually how to think about the readiness and appropriateness of your infrastructure for a complex machine learning system. Because nowadays, machine learning is not just a script that you submit in batch mode and magically returns some solution. Nowadays, machine learning systems are very complex pipelines, as I mentioned very, very early. It includes ETL processes, storage to databases, data aggregation, cleaning, training. Probably you're serving it as a REST API or things of the such. So the first thing that you have to test is the reproducibility of your training. If you are training your model 2 times or 2 models in the same environment, try and check for differences on aggregated metrics. Try and find differences in example predictions. If it turns out that these differ a lot, you'll have to debug your code, but also your environment and your infrastructure, because this can lead to non-deterministic deployment. Also, run integration tests across your entire pipeline. Let's say that I have a model, version 1.0, and I have to release version 2.0 because I have made substantial changes to my code base. Test again across the entire pipeline. How does it integrate with my data ingestion and data preparation stages? How does it actually serve and behave with our fully deployed solution that is reaching our customers? You have to think about all of this. And also, sometimes you might want to have 2 versions of the same model running in production for a while, so you can actually test the performance and the one-to-one accuracy between these 2 different versions. So every time you change any of these moving pieces, you have to test them in conjunction with the pipeline. It's not enough to just test them as isolated units. But also you need to test against data with known outputs. And this means that you should always have a baseline data set that you can test at all times. You should be knowing what you're expecting, again, of your data and your model at all times. So if you don't have a baseline data set or a baseline testing strategy, then basically you're deploying in blind. And also a very, very, very important thing is test how quickly you can roll your models. And this refers not only on how fast I can take a new model to production, but also how fast I can take a model down. Imagine this very common scenario. You develop a model, you develop a new prediction system, you put it into production at 3 o'clock in the morning, and it starts failing probably around 5 o'clock. Your infrastructure people are in a congress or in a conference, and then there is nobody that can take it down. You have to have measures so that it's as easy to deploy as take down models or roll back to previous versions. So you also have to test how efficient and how timely are all of the solutions that you have in place to deploy your models. Also, if you're expecting to have a surge in your customers, like so, you also have to test how easy it's for you or your solution to scale up your resources. And this takes us to creating a very clear rubric. And again, I've given a lot of recommendations in 3 stages that are data and features, model deployment and model development, and finally infrastructure that covers the entirety of your pipeline and your systems. But probably you'll have to have more steps, additional tests, depending on your use case, depending on the type of industry you work, if it's highly regulated, if it's not as highly regulated, but it's continuously generating new and new and new streams of data. So let's go back to this very initial rubric that I mentioned at the beginning. I ask you to assign in your head or in a notepad or somewhere 1 point for any of these steps or these tests that I was talking about that you were doing manually. A second point was going to be assigned for any sort of automation. So let's say that if I was already checking my distributions manually, but then I had a script that will further confirm the distribution of my features every time I push code to GitHub or GitLab, then that gives me 2 points. So you have to aggregate all the points per section for data, infrastructure, and deployment. And the final score is going to be the minimum of these 3 stages. Because this is going to tell you which is your weakest link in your machine learning system. If you have a very poor score when it comes to infrastructure readiness for machine learning, that's where you have to put more resources and more effort. If you're having just about as equal scoring in the 3 areas, then you can distribute your efforts depending on what is the most urgent needs for your company or for your research institution. So you can think that if you have 0 points in any of these 3 areas, whatever you're creating is not production ready. So you have to invest a lot of human resources, probably infrastructure resources, and a lot of time to get this to a certain standard and to a certain level of quality. If you accumulate 1 to 2 points, probably you have some reliability holes, and you have to find where you're lacking this quality assurance and start patching and start sending efforts there. 3 to 4 points will give you a reasonably tested solution. That means that it can go into production, but further iterations are going to be needed, further refinement, and there is always the risk of you finding big bugs. 5 and 6 points indicate some sort of good level of testing, good level of monitoring. I didn't touch that much on test monitoring, but it gives you a good, healthy machine learning system. It gives you something that can be reliable, robust, and you can focus on targeting the most urgent bugs without the fear of everything exploding anytime soon. Finally, if you have 7 or plus points in your weakest link, then that means that you have very strong levels of automated testing and monitoring. And this is what we should all achieve, aim for in data development or deployment and infrastructure. Every time I work with a new team and we talk about this, it is a lot of work. It comes like a lot of work, and it comes like a lot of effort. But it is something that really pays off in the long term. It's going to be a lot of investment in terms of resources and time and effort and driving very, very complex and not so nice conversations with your teams. But in the long run, it's going to pay off, not only for you, but for your customers, and especially those that are then applying for subsequent rounds of funding. Having a clear quality control and quality assurance rubric helps a long way. So I really want you to take this back to your teams, take this back to your research institution, to your teams, and do a soft evaluation on what you could do better, what areas you can do better, and what you're doing already good, already well. And if you have any questions or you want to chat a bit more about this, feel free to contact me. And that's it. Thank you very much.
All right.